to do one more Newton's second law problem with friction. So we're probably getting pretty good at the Newton's second law problem solving strategy. So I'll ask some questions that particularly focus on the friction here. So we need to think about the friction, but it is just a Newton's second law with friction. Okay, so let's just take our book and let's put it on a ramp. Say that we're, I don't know, doesn't matter. Trying to think of what you're using a delivery system to move your book from one place to another. We're going to put it on a ramp, but the ramp has friction. So let's say your book has a mass of 5 kilograms, and the ramp has a static coefficient of friction of 0.6, and a kinetic coefficient of friction of 0.4. Let's say that the ramp angle is 25 degrees. Okay, just making up these numbers. If I put this book on the ramp, first question is will it move? So I'm just putting it on the ramp. I'm not giving it a push, just putting it on the ramp. Will it move? And the second question is, if it will not move, how hard do I have to push to get it going? And the third question is, if it does move, or if I have to push it to get it going, will it keep moving? Or how fast does it accelerate? So let me write those down. Okay, so here are the questions. Will it move if the initial velocity is 0? In other words, will it start sliding on its own? If not, how hard would I have to push to get it moving? And then, if so, we can just move straight to part C. What is the acceleration? If not, once I give it a push, or even if it starts moving, will it keep moving? Now, CI is really just a subpart of C. What we really need to do in part C is to find the acceleration in order to ask the question, will it keep moving, is to find the acceleration. So I'm sort of giving away part of the way we find C, but really the question is if it does move, what is the acceleration? Okay, let's answer these 3 questions. Let's do a Newton's second law problem. So without even wondering about how to answer the questions, let's go ahead and at least set this up as a Newton's second law problem, because it's about forces and about motion. Okay, so we've drawn a diagram, and on that diagram I'm going to draw my coordinate axis, and I'm going to draw plus x pointing down the ramp. You say, how do I know it's pointing down the ramp? I don't know if the box is going to accelerate down the ramp or not, but that's going to be the direction of motion. So since I don't know the direction of acceleration, whether it's up the ramp or down the ramp, you might say, of course it's down the ramp. Careful. If it's slowing down on the way down, the acceleration is up the ramp. But anyway, I'm going to choose down the ramp is plus x, because that's my guess on the direction of the acceleration, right? My guess is that it's accelerating down in that direction. And so plus y is going to be perpendicular. So I've drawn a diagram. I've indicated my axes. I could probably put a few more things on the diagram, but I'm not sure. So then I want to write down Newton's second law, which shows that that's how I'm going to solve it. F net equals ma. I'm going to break everything up into components so that F net x equals max and F net y equals may. Again, showing that I know it's a two-dimensional problem. So, but what didn't I do? I left out the step 3-ish or whatever it was, draw the free body diagram. Let's go ahead and draw the free body diagram. So I did my steps a little bit out of order. And is there a normal force? Yes, there's a normal force perpendicular to the contact surfaces. Is there a rope or string attached? No, there's not a rope or string attached. So, tension. Is there gravity? Yes, gravity is straight down. Be careful with these ramp problems to make sure to pay attention to the angles. Fn is angled, Fg is straight down towards the center of the earth. Is there, and going through my list of forces, springs, no strings, is there friction? Yes, there's friction. What is the direction of the frictional force? Well, the body is trying to move down the ramp, right? So I'm going to do separate from the free body diagram. We're going to say the motion, intended motion, is in that direction. So the frictional force has to oppose that motion. The frictional force is in that direction. Notice that if I were to push, I asked how hard I should push to get it moving. That's implying, maybe I didn't say it clearly, but that's implying I want it to slide down the ramp. So if the intended motion is down the ramp, that's my velocity going down the ramp, then the frictional force opposes that and it's up the ramp. If the question actually asked me about pushing the box up the ramp, if I was pushing the box up the ramp, so this is just an aside, it is not this problem, if the intended velocity was in that direction, then the frictional force would oppose it, would be in the other direction. Remember, the frictional force opposes the direction of motion or the intended direction of motion. Okay, so let me go back to this problem. This is the complete free body diagram for this problem. The velocity doesn't belong on the diagram. That's just there to show that we know the direction of friction must oppose it. Okay, so this is the free body diagram, and so now I need to take components of everything in the x and y direction. So I'm going to go ahead and superimpose my x and y axis. This is my plus x direction. This is my plus y direction. Superimpose that on my free body diagram so that I can see in the x direction that f net x has a component of fg, right? A component of fg is in the x direction, and fg also has a component in the y direction. So I'm just drawing those components. I'm not supposed to draw those in the free body diagram, but since I've got colors, I'm saying the free body diagram is purple. The orange, I'm just taking the components. I would really prefer you to draw a separate diagram to take the components. But f net x has the component of fg sub x down the plane, and ff is up the plane, and it's entirely in the minus x direction. F net y, again from my free body diagram, plus fn is in the plus y direction, and minus the y component of g is in the minus y direction. So let me go ahead and draw that on a new page just to make sure we see that. First of all, notice fn is in the plus y direction, ff is in the minus x direction. Those are easy, but it's the components of fg that we got to make sure that we're getting those right. Here's my box on the plane. Fg points in this direction, so there's going to be an x component pointing down the plane because this is plus x direction, this is plus y direction, and there's going to be a y component pointing perpendicular to the plane. So drawing my axes, I'm going to draw yet another picture. Drawing my axes at the correct orientation, Fg points down from the origin, and to take the components of Fg, I've got to have the component in the x direction and the component in the y direction. They have arrows, right? They point, the component in the x direction points in the plus x direction, component in the y direction points in the minus y direction. Fg sub x, Fg sub y, and then we've got to do geometry, and the geometry is we've got to find one of these angles. Let's say this angle, compare that to the ramp, right? This is the ramp, remember? This is why it's helpful to look at both pictures. This is the angle theta. So the other angle that I've drawn in here, which I'll now make red, is not theta. Right? That's this angle here, and that is 90 minus theta, where theta was 25 degrees. So that is 90 minus theta, which is 55? 55, nope, 65. 65 degrees. The magnitudes of those two components are Fg cosine theta 65 degrees and Fg sine 65 degrees, where Fg, remember, is just mg, and m is given, g is 9.8 meters per second squared. So those are the components. Notice that if you had chosen to use the bottom angle instead, which is 25 degrees, then you would find, so you might have written down instead Fg times the sine of 25 degrees, and Fgy is Fg times the cosine of 25 degrees. So it depends which angle you're using. Both of these are correct. Either set of these components is correct. Back to my free body diagram and say, okay, so now I've identified Newton's second, actually I'm going back to Newton's second law. I've identified the net force in the x direction and net force in the y direction from the free body diagram. It's over here. I'm going to redraw that, rewrite that. I've just rewritten Newton's second law, plugging in just the left-hand side, just not paying attention to anything else, plugging in the left-hand side. We get that and that from the free body diagram, where rather than me plugging in numbers, I'm just saying, oh look, I know Fgx and I know Fgy. I know those things. I figured them out. Now, what else do I, now I look at the right-hand side. I know m, and a sub x is unknown, but a sub y is 0 because I've chosen x as the direction of motion. So a sub y is 0. The book does not pop off the plane. Okay, so we can rewrite this as, so that's as far as we can get using Newton's second law. And I'm using letters just because it's easier. It is actually easier to use letters than numbers, but I am plugging in theta equals 25 degrees just so that we don't get confused about which angle we're talking about. Okay, I guess I could have just wrote theta and said we're using, in that case, theta is 25 degrees. Okay. Now, I've gotten as far as I can with Newton's second law without even thinking about the question's asking, but what is the question asking? The question is asking, will it move if the initial velocity is 0? Will it move? How do I answer that question? I made, so actually I didn't make an error. So the question really is if it starts from rest and it's going to move, then the acceleration would have to be greater than 0, right? That's what question A is asking. Is a sub x greater than 0 if v0 equals 0? That's what it's asking. And so then we got to say, oh, what do we know here? Well, in order for a sub x to be greater than 0, this value has to be bigger than this value because it's one minus the other, right? And so then we say, we're asking, have we overcome the static friction? So that's why I didn't put a subscript on the friction, because if it's not moving, it's static, and if it's moving, it's kinetic. So have we overcome the static friction? So we need to, in order to show if it's moving, we need to say the downward force has to be bigger than, the upward force along the plane. And so in order to answer question A, we need to ask the question, change my color. Question A is really, is mg sine theta, where theta is 25 degrees, greater than FFS max? Is it big enough to get it moving? That's what we're asking. Is it big enough to get it moving? That's what we get out of this equation. So we then now we recognize that's the question we're asking. We go ahead and plug in for FFS max, which is mu sub s Fn. We say, is mg sine theta greater than mu sub s Fn? We say, ooh, what is Fn? Mg, right? No, it is not mg. Fn is a quantity that we have to solve from Newton's second law, but look, right here. We know Fn from the second equation, from the y equation. From the y equation, you can see that Fn is equal to mg cosine theta. So therefore, to answer part A, it's, is mg sine theta greater than mu sub s mg cosine theta? Again, we're asking, is the downward force, the component of mg pulling down the plane right here, greater than FFS max, which it turns out is equal to this because of the definition of FFS max and the fact that we can solve Fn from the y equation. Okay, so that's really the question we're asking. And if I didn't plug in numbers up till now, notice I did replace 25 degrees with theta and just saying, look, remember we're talking about that angle. I do this on purpose because look what happens. The mg's cancel. We don't have to plug in those numbers. It's just going to mess us up. So it's a question of, is sine theta greater than mu sub s cosine theta? Now it's a plug-in. Now I plug in the numbers and I get down to asking, is 0.71 bigger than 0.55? The answer is no. So what? So the downward force is not big enough to get it moving. It doesn't move.